Okay, hi and everyone. Today's presentation is about the pathology, and the paper title is Discovering Pathology Rationale and the Token Allocation for Efficient Multimodal Pathology Reasoning, and which is research started by the Google group. And okay, so as well. Okay, so here is the background for this pathology, for the pathology image, and as we can see, the digital pathology image is obtain the corresponding humans lesion region from the human body, and they utilize the scanner to digital this samples and utilized for tumor diagnosis. And this is a digital image, and the data format can be look like this one, and it is characterized by his gigapixel features, which means as we can see this whole slide image, it can be patched into maybe billions of patches, and each patches can be obtained the corresponding image features. And this patch maybe can be viewed as a 256 squared image patch. So as we can see, this whole slide image can contains gigapixel image space, and so and the host how to utilize this whole slide image to do some clinical analysis. And as we can see, this first we will utilize these gigapixel features and patch into or slide cluster into multiple patches and stuff like that. After that, we only have the corresponding slide level annotation usually. So we utilize these patch images and to fed into foundation models and encode the corresponding patch level features. And after that, we have to jointly utilize such enormous patch level features to predict slide level levels. So the weak supervised signal is very weak. So this is the current single model's image analysis for the whole slide image. And however, the real world pathological diagnosis is seldom limited to visual assessment alone, and it often involves integrating information from diverse sources, such as clinical notes and the patient history and stuff like that, some textures, books, and other modality. So however, current pathology vision large language models struggle with the real diagnostic reasoning, and they often memorize superficial correlations between the host image and the diagnosis result. And we also have to pay attention for their efficiency, because the host image exists gigapixel level images. It is too much vision tokens for the current vision large language model. So this paper, they propose a bilateral reinforcement learning framework simultaneously enhance diagnostic reasoning and optimize the computational efficiency. And as we can see these two figures, the first one, they utilize the soft supervised fine-tuning as well as the GRPO to increase or to enable the model the reasoning ability. And the second one, they utilize a token allocator, also trained by GRPO to allocate the token budget. Okay, and as we can see this overview figured in the training phase, the vision language model will receive the input image and the corresponding input prompt which may describe the corresponding pathological task. And after that, the task performance will be trained by SFT as well as the GRPO for multiple downstream tasks, including subtyping and detection, which means detect the tumor region and the vision question answering, including the open-ended and the closed-formed. And simultaneously, they will utilize a token allocator, which receive the image token and the corresponding prompt again, and try to automatically allocate the corresponding token budget, such as, for instance, in an easier task, it will tend to allocate a lens token for this image, and in contrast, a harder one, it will allocate maybe a maximum token budget. And during the inference phase, and when we got a test input image and the corresponding task, it will utilize this token allocator first. It will comprehensively evaluate the complexity of this task and determine the number of the tokens. And after that, it will utilize this task performance to reasoning the corresponding answer based on the input text and the image. And let's take a closer look into the detail of this methodology. And first, in the first part, and for the task performer, it will utilize a two-phase paradigm to train a task performer with low rank adaptation, which LoRa, right? The first one, it will utilize the supervised fine-tuning to establish a robust feature representation and the task-specific baselines, because it utilizes a general vision language model, so they don't have enough specific clinical priors. So the first step, they utilize SFT to establish such a capability. And after that, it utilizes a reinforcement learning through the GRPO and based on a specific reward functions tailored to distinct pathological tasks, including VQA, cancer subtyping, and lesion detection. And for the reward function, they defined as the reward for corresponding task plus with the reward for the format. For the format reward function, they will enforce the model to put into their syncing process and the answer between the syncing format and the answer tags, respectively. And for the corresponding specific tasks reward, first for the VQA reward, it utilizes this answer reward to comprehensively measure the accuracy of the corresponding answer, especially for the closed end. They will utilize the ACC, and the open-ended, they will utilize the blur score. And for the subtyping, it is a multi-class classification. So it will utilize the ACC reward, which means when the prediction answer is equal to the ground truth, they will give it will give the reward 1. Otherwise, it will give them 0. And for the detection it will detect the corresponding bounding box. So it utilize this average precision reward, which means they measure the predicted bounding box and the corresponding ground truth ones, and average all of this precision to obtain this reward. And okay, So let's go to the token allocator. And this dynamic token allocation, it convert this paradigm into as a reinforcement learning problem. So they trained the LoRa to optimize the trade-off between the computational efficiency and the diagnostic accuracy, which means they design the corresponding reward and like this format. So MP and N0 indicates the predicted token count and the corresponding original token count. So when the predicted token count is greater than the original one, it will penalty the corresponding task's reward, which wherein the alpha is a scale equal to 0.5. So if we want to generate the longer predicted token, we have to increase the corresponding reward function, which means you have to achieve a better performance for these tasks. Otherwise, this allocator will tend to allocate the number of token less than the original token count. Okay, so after that, they evaluate the model on 6 public datasets, including across 3 tasks, which including the VQA tasks and the subtyping tasks and the legend detection tasks, and also evaluate such benchmarks across different corresponding metrics. For the BQA, they utilize the accuracy for the closed-ended answer and the blur for the open-ended one. And for the subtyping, they utilize the balanced ACC and the weighted F1 because of the imbalanced classification for this task. And for the detection, they utilize the mean average precision and the intersection over union. And also, as they utilize the token per image to calculate the corresponding computational efficiency. So for the first task, the VQA task, they evaluate the model on two datasets. For the past MMU dataset, it includes different specific tasks, and so they evaluate the specific metrics and as well as the overall metrics, as we can see. And so at first, after SFT, we can find the 7 billion can own the corresponding specific knowledge to correctly answer the answer to correctly predict the answer. And after that, they utilize the task performance, which means they utilize the GRPO to enrich the model, the corresponding reasoning ability, and we found this one with the task performance, it increased the overall performance and reach a comparable performance across specific tasks. And after that, they add on the corresponding the token allocators, as we can, and they found the overall it can achieve the best overall performance as well as the comparable performance on specific tasks, and especially it reached a lowest TPI score, which means it has the best computational efficiency. And for this past BQA dataset, they also because the other foundation model didn't have such ability, so they just compare it with the general baseline model, and they found the performance, the model with performance and the allocators can achieve the best performance and achieve the lowest TPI, and as well as the corresponding reasoning ability. And for the subtyping task, and again, they found after SFT, it can enrich the general model, the specific priors, and after that, when they utilize the GRPO and the allocator, they can achieve a best weighty F1 score and the lowest TPI score. And for the detection tasks, they also evaluated on two datasets and found the model with performance and the allocator can achieve the best accuracy and the best and the lowest TPI. And yes, again, sometimes they found the model with performance can achieve the best single metrics, but when they add the allocator, token allocator, they can drastically decrease the corresponding TPI score. So after that, they also do an ablation study to start to test the effectiveness of the token allocator. So MHAT is the max token budget. So image with original token number greater than the MHAT will be downsampled. So as we can see this table, in the model with task performance and with a fixed max token budget, they can achieve somehow superior, somehow better performance than the one with greater max token budget, like MHAT is equal to 512 and or 1024. And after that, if they utilize the allocator, which means they don't have such a max token budget, and the model will dynamically allocate the token budget. They found that this version can achieve the best performance across such a different diverse specific tasks, and especially it will drastically decrease the corresponding TPI. And okay, so here is a qualitative example for this model. As we can see, the first one is a close-ending VQA task. It will give the 4 options. So after SFT, for the Chenwen 7 billion, it answer the correct answer. It will generate the incorrect answer, but after enable the model have the reasoning ability, it will think it and predict the correct answer. And also in the open-ended VQA, the SFT cannot also predict the correct answer, but after thinking, you will know this task is very, very easy, to do, and somehow it will allocate a lens lens token count and generate the correct answer. And for the detection also, and after the task performance, it can generate the correct bounding box. Okay, and now here we come to their limitation. And in this paper, they only use a 7 billion Chen model, and due to the computational constraints. And after that, due to the resources limitation, and they have to limit their analysis to a large ROI instead of the whole slide image, which means they didn't utilize the gigapixel feature space. They only utilize maybe 248 squared patch image to generate the corresponding answer. And also in this paper, I think the larger scale data set is needed for further validation. So here is some takeaway for this work. So this work is the first reinforcement learning paradigm that enables model to learn pathology rationale implicitly from the labels. And it introduced a bilateral RL framework with two branches, one for pathology reasoning and one for adaptive token allocation. And it achieved 41.7 performance again while cutting token cost by 70% across VQA, subtyping, and the task and detection tasks. But however, it is restricted to patch level tasks instead of the slide level ones due to computational constraints. And okay, so here is my today's presentation. Thanks for your listening. Yeah.